Good evening, everyone. Thank you for joining. So in week 9, mainly some of the classical machine learning algorithms are used because still some of them are the best techniques that are used for many real world applications. And also there are freely available implementations of these classical machine learning algorithm in many packages. For example, in scikit-learn, R packages, etc. And they are widely used in data analytics, medical imaging, and engineering. Um, and before this, AlexNet uh, usage for image analysis, random forest were the dominant tool that was used for medical image analysis. So mainly in this week, the algorithms such as KNN, which is a supervised classification technique, then decision trees, which is again a supervised classification or regression uh, trees, and then bagging is discussed, which is an ensembling method. And then random forest is discussed, which is a ensemble method again. Then there is the boosting, which is again an ensemble method, and then gradient boosting. Um, and then k-means clustering, and then agglomerative clustering. So k-means and agglomerative clustering, these two are two of the unsupervised technique. Now coming to k nearest neighbors algorithm. Here, this is one of the simplest supervised classification algorithm. It doesn't have a training step, and the entire data set is loaded into the memory, and predictions are made at the inference time. So, what is the main concept in KNN is that you find the k closest training examples and assigns the majority class among this k nearest neighbor. So it finds k nearest neighbors and assigns a majority class found in this k neighbors as the prediction or the class for that or the class for that particular data point. It doesn't have any training. All the computation happens at the prediction time. Um, so the steps are as follow. Like first we find the nearest neighbor and assign its class. And so we don't know what is the uh, value of k. So this is like uh, how many nearest neighbors should we consider for voting. It shouldn't be too small. Then, for example, if k is 1, then it will result in very sharp jagged decision boundary. That means it will result in overfitting. And if k is large, the boundary, there is only one majority class. Like, for example, when k is n, which is all the data points, then it is underfitting. It predicts only one class, which is the majority class. So, what is the optimal k? We treat k as a hyperparameter, and we find what this k is through cross validation. So, for choosing the k, we keep a validation set, and then we vary k from 1 to some maximum value, and then we select the k with the best performance on the validation set. Now, um, here in the case of k nearest neighbors, we find who is near to us. So distance is a metric here. But before we calculate the distance, it's important to normalize the features. Since features will have a different scale, it is important to normalize. these features before calculating the distance. So for KNN, there is no training required, and only thing is that it is very slow at prediction time, because at the time of prediction only it will compare the given data point that is in testing with all the existing training points. So it is best used when there is a moderate sized data set where interpretability is not that critical. So this is about KNN. Now coming to decision tree. So decision tree makes prediction by splitting the training data based on the feature values. So it builds a tree structure, and then finally it makes a prediction based on what its leaf node predicts. So based on what the prediction is there in the leaf node. So there are in the tree structure there are certain components. One is this root node. So root node is the this is where the first split is made. This is the contains the entire data set. And there is the internal node. So internal node is where the intermediate split happen based on a feature threshold. And then there is a leaf node. So leaf node is where the final prediction is done. It contains ideally only one class. And then the decision boundary is the boundary in the feature space separating these different classes. And depth of the tree is number of levels in the tree. Now, at each node, we choose a feature and a threshold to split the node into, or the data into two groups. And all data points that satisfy the condition go to the left side, and all the data points that violate the condition will go to the right side. And we repeat this until all the leaf nodes contain one class or maximum depth is, or we can specify this many levels we need, or we say some stopping criterion. Uh, so this is how the split works. And then splitting criteria is we want the splits that maximally separate the classes. So few of the matrices or criteria that are used for maximally separating the classes are classification error, entropy, Gini index. So classification error is it's like 1 minus the proportion, maximum of the proportion of classes. It can like it's a very it's not very widely used, and it's a very poor splitting criteria. Two of the most commonly used are this entropy and Gini index, but classification error is also used, but it is not generally a recommended one. Entropy is when the entropy is said to be zero when the node is pure. Like when the node is pure means it will not contain, the node will not be confused about which class it is dealing with. And entropy is maximum, like entropy is 1 when the classes are equally distributed. So choose the feature plus threshold that gives the maximum decrease in entropy. That is the splitting criteria for entropy. So we want to reduce the entropy. Entropy is something that characterizes uncertainty. So when the entropy is high, it means that there is a mix of many classes. But when entropy is zero, it means that there is a clear separation. So that is one criteria. Then Gini index is 1 minus the cumulative sum of probability of classes raised to square. So the maximum Gini index is like when the class is um, like when the class is a or when the node is a pure node, the Gini index will be 0. And when there is equal probability between all the classes, then the Gini index will have the maximum value, and that is equal to zero point 0.5. So these are the few of the splitting criterion. Uh, Okay, so we always start at the root with all the training data, and then for each node, we try every feature, try every threshold, and calculate the information gain, that is this entropy or Gini index, and then assign the data to the left or right child node. And then we repeatedly do this till some stopping criterion is reached. And at test time, we pass the data point towards the tree from the root, follow each of the split, and then finally we reach a leaf node, and then we output the leaf class. So for impure leaf nodes, we use the majority voting. Yeah, so the k is odd number. um because you want to take majority voting. So, for example, if there is class, uh, there are two classes, class A and class B. If you set K as 4 and you get two voting for class A and two voting for class B, then it's a difficult, like there's a difficulty to finally conclude which class the new data point belongs to. So it is better to have an odd number. And the case value selection criteria, as I told, is a hyperparameter selection method. So here you use some cross-validation technique. You don't know what K is good for your data set. So we always try for different values of K using some hyperparameter optimization, and then we find the value of K. So it's not like K is equal to some odd number, let's say 5 is the value for all the data set. We always have to find it using some grid search. Okay, so that is decision tree. Then the same thing we can do with regression task as well. So regression, so again, it gives continuous output prediction. Um, and it will partition the input feature space into region, and there will be a constant output value to each region. Uh, so again, it's the same like this um, classification tree, but then the difference is this it deals with regression than classification. So then coming to bagging addresses the high variance problem of individual decision tree by training many trees on different bootstrap samples of the data and aggregate their prediction. So if so individual decision tree might give you some output, but then that may not be always correct. So uh, there is a high variability that can happen with individual decision tree. So what is done is we train multiple trees on different bootstrap samples and then aggregate their prediction. Uh, yeah. So here bootstrapping is basically you sample with some replacement. So if you have n balls, you take 3 balls from it, but you also replace it, and then you again sample from the same set. So that is sampling with a replacement. So in Bagging, it's mainly a bootstrap aggregating. So you create multiple bootstrap samples and then train these on multiple trees and aggregate their prediction. The problem with single decision tree, as I told, is they will perform well on training data but poorly on unseen data. There will be a lot of variance, and to reduce this, a robust approach is to use this bagging, that is bootstrap aggregating. Um, you can sample if you have n data points. Some point will appear multiple times, and some will not appear at all in case of bootstrapped sample. And then, suppose if we do this bootstrapping b times, we get b such data set, and we train one decision tree per data set, and then we aggregate the prediction. So in case of regression, what we can do is we can take the average of the values that we get from each of the decision tree. In case of classification, we can take the majority vote among the uh, different trees. If it is probability, then again we can average the probability. So this is bagging, and random forest is one such method that uses the concept of bagging, but it also uses one more thing, which is randomizing the that is the difference between bagging and random forest is that both will bootstrap samples of data, which is same in both cases. And in case of bagging, all the features are considered at each split. But in case of random forest, only a random subset of features are considered at each split. So as a result, in case of bagging, all the features are same. So the trees may be correlated if one feature is dominating, but in case of random forest, the trees are decorrelated. That is because we use different features at each node. So at each node in the tree, in each of the tree, we randomly choose, if we have n features in total, we randomly choose d features out of that n features. And typically this d value that is used for classification is square root of n if I have total n features. And for regression, so this is for classification. And for regression, it has been found to be around n by 3. So these are some of the values that are found with different data sets. So it's square root of n for classification and n by 3 for regression. Okay, so then as I told, in the end, we use majority vote all among all the trees or average output among all the trees, depending on whether it is regression or classification. Now, in case of boosting, what happens is it improves the prediction accuracy through a fundamentally different strategy than bagging. That is, it mainly focuses on the samples that were previously misclassified. So we will have sequence of weak models, and in each subsequent learner focuses more on the mistakes of the previous one. So the final prediction will be a weighted sum of all the weak learner prediction. So usually what is used as a weak learner is this or a base learner is this decision stub. It is a tree with one node. which is split into two groups. So very weak classifier this will be. So when we have a sequence of such classifiers, it can become a strong classifier. Now, in case of ADA-boost algorithm, we assign an equal weight to each of the n training data points. We then fit a classifier, a weak learner, to the weighted training data. We compute the error. We compute the classifier weight, and we update the weight. So based on uh, misclassification, if there is a misclassified point, then that is assigned more weight. So there is so this is what is done with ADA boost. Um, Now there is a loss function that is used in ADA boost, which is an exponential loss function. So it sequentially focuses on the samples that were previously misclassified. Now coming to gradient boosting, it instead of the exponential loss function here, we can use any differentiable. Here we can use any differentiable loss function. So here instead of updating the weights, before we were updating the weights of the misclassified sample, but then here we update the prediction by fitting a model to the negative gradient of the loss function. So in each iteration, we compute the gradient of the loss with respect to current prediction, and then we fit a regression tree to approximate this gradient, and then we update the model. So there's a learning rate as well, which is used to find this update model updation, that is which is given in the lecture. So for each iteration, we compute the gradient, we fit a decision tree, and we find the optimal step size, and then we update. Uh, yeah, so you can use many different types of loss function. It is not just exponential function, unlike the AdaBoost algorithm. Um then coming to the two unsupervised technique, K-means is an unsupervised learning algorithm that groups the unlabeled data into K clusters by minimizing the within cluster variance, that is the within cluster distance. So in unsupervised learning algorithm, there will not be any labeled data. So we are given some raw unlabeled input, and we have to find the underlying structure or the grouping in the data. So the model has to automatically determine what is the pattern or a distinguishable structure inside the data by using a defined metric. Now these are used in many applications, such as, for example, you want to segment customers based on their buying patterns. That is one example. Then, so here you will be, what you have to do is you have to minimize the within cluster distance between the, you have to maximize the distance between the different clusters and minimize the within cluster difference. That is the main thing. So we start with choosing K cluster senders. So we'll have a set of data points, and among the data points, we start with randomly selecting a cluster point as the cluster sender. And then for each data point, we compute the distance of this point to all the other data points. And then for each of the data point, we compute the distance and we assign each of this point to the nearest cluster. So we have k different clusters which we randomly select, and then from each of these senders that we have randomly selected, we have to find the distance from these points to all the other data points and add them to the cluster to which they are near. Now, then once we added all of them to or assigned all of them to some nearest sender, we have to update. So for each cluster, we recompute the sender as the mean of all the assigned points. Then we repeat this until we don't see any change in the cluster. I mean, the same set of points belongs to a certain cluster is not changing. Then at that time, we stop the algorithm. So one issue with k-means is that it is highly sensitive to the initial cluster sender placement. So different random initialization can produce different clustering senders. So one solution is to run k-means multiple times with different random initialization. And then choose the result with the lowest total within cluster variance. Uh, that is one way to do this. Then choosing the right k, again, like in k nearest neighbors, in k means as well, k is a hyperparameter. You have to find the value of k. One way is to plot this within cluster distance to different values of k. And if we find an elbow, that is this point, where there is like maximum curvature, this point can be selected as k, the optimum k value, after which the curve kind of flattens. So this within the point where adding more clusters will not yield any good performance is where we find the elbow. So that is one way to find the k value. Yeah, so that is K means clustering. Then coming to agglomerative clustering. So this start, it's a bottom-up approach. We don't have to specify uh, any K value, but it will result in something called as a dendrogram. So initially we consider each data point as its own cluster. So if I have n data points, we imagine that or we assign that there are n clusters. Then we repeat n minus 1 times, find the two most similar clusters, with the smallest dissimilarity, and then we merge them into one new cluster. Then we update the dissimilarity matrix, and we keep on doing this until we have one cluster containing all the data points. So the result of this is a tree-like structure called as a dendrogram. Now, while merging the clusters, we need to measure the distance between the clusters, and this is called as linkage. So linkage is, there are different types of linkage: single linkage, complete linkage, average linkage, etc. In single linkage, it's the minimum pairwise distance between the elements of two clusters, and complete is the maximum distance between two clusters, and average is the average of all the paired distances between the elements of the two cluster. So in case of dendrogram, the x-axis will always have the data points, and y-axis is the cluster distance. And as we move up, the dissimilarity increases. Then we have more dissimilar clusters being merged. So these are the things that are discussed in the week 9 videos. I hope all of you have watched the lecture 9 videos. Now coming to some of the previous year assignment questions as well as some practice questions. Okay. So the question is, bagging trains many trees on bootstrap samples. Why does using bootstrap samples help? Bootstrap samples contain more data points than original data set. Each bootstrap sample is a different random subset with replacement, introducing variation. Bootstrap samples automatically remove outliers. Bootstrap samples are always perfectly balanced between classes. So, bagging um, uses bootstrapping and aggregating. So sampling with replacement means that each bootstrap dataset is slightly different, causing each trained tree to be different. So this diversity is what is making the average effective. That is, more diversity can cancel out each other's error. So each bootstrap sample is like a different random subset that is used with replacement, and that will introduce this variation. So with each bootstrap sample, each trained tree will be a different kind of a tree. In KNN, what is the effect of setting k is equal to 1 on decision boundary? Very smooth boundary, likely to underfit. Very jagged boundary that perfectly separate all the training points, but it is prone to overfitting. A straight line separating two classes, no boundary formed, every test point is classified as majority. So here it will be a very jagged boundary that will perfectly separate all the training points. But the issue is when a new data point comes, it will be prone to overfitting. What happens when k is set equal to the entire training data set? A, every test point is predicted as majority class. B, the model achieves good discrimination capability. C, the decision boundary is complex. D, the decision boundary will be a straight line separating the two classes. So when k is set equal to the entire training data set size, every test point is predicted as a majority class. Before computing Euclidean distance in KNN, why is feature normalization essential? Normalization is only needed for categorical features. Without it, features with larger numerical ranges dominate the distance calculation. KNN only works on binary features. Normalization removes duplicate data points. So without normalization, the features with larger numerical range will dominate the distance calculation. So for example, if there is one feature which has values ranging from 0 to 1000 and there is another feature which has values ranging from 0 to 1. So the distance will be almost entirely determined by the first feature which has large value 0 to 1000. So the normalization, if we do, it will make all the values to the same range. For example, 0 to 1. Then everything will get equal importance. One will not be dominated by other. Why might an even value of k cause problems in binary k-NN classification? Why might an even value of k cause problems in binary k-NN classification? Even values of k cannot compute distances correctly. They may lead to ties where exactly half the neighbors vote for each class. Even k value make the algorithm slower. Even k value overfit the training data. So with k is equal to 2 or any even value, there is a risk of 50-50 tie. So in that case, the prediction is like it's not clear which one is the correct value. So odd, if we use odd values, it will avoid this problem. So which is the optimal way to select the value of k in KNN? Use the square root of number of training samples as a fixed rule. Use a validation set or n-fold cross validation. Which is the recommended approach to find k. Yeah, so we have to use a validation set or enfold cross validation. So why does random forest randomly select only a subset of features at each node split rather than considering all the features? Why it doesn't consider all features? So to speed up computing by reducing the search space, to decorrelate the tree, that is, if one feature dominates, then all the trees will split on it. To guarantee that every feature is used exactly once across all trees, because using random features allow it to converge. So, random forest uses different features at each node because if one feature has the highest information gain, then all the trees in bagging will split on it. That is, if one feature is dominating, then all the trees will split on that node. But then all the trees will be identical. They will be correlated, right? If there is one feature that is dominating and every tree is using that feature, then it means every tree is identical or correlated. So random feature selection will force the tree to explore different features. Thus, it will reduce the inter-tree correlation and it will reduce the variance. So that is why the main thing is we want to decorrelate the trees by selecting only a subset of features at each node, and they will be random. So in a dataset with 100 features, approximately how many features should the random forest select at each node for classification? 100 all the feature, 50 half the features, 10 which is root of the number of features, 1 only a single feature. So the standard rule of thumb for classification is this number of features is square root of n, which is the total number of features. N is the total number of features. This is standard thumb of rule. So when n is 100, d will be the square root of 100, that is 10. So it has been found that this will balance the low correlation against a good predictive accuracy. So this is why this root of n is taken. So for aggregating predictions in random forest regression, which method is used? Majority voting, taking the median of the outputs from tree, averaging the outputs of all tree, using only the single tree with lower training error. So for regression, we know that the prediction are real numbers. So it is the average across all the trees. So for classification, we use majority voting. Okay. For a binary classification problem, at which class distribution does entropy reaches its maximum value? When one class has 100 percentage of data points, when both have 50 percentage of data points, when the minority class has exactly 10 percentage of data points, entropy has no maximum. So you can, mean is one of the most commonly used for regression, for aggregating the outputs from different random trees. We can use median also, depending on the data. Uh, so it's just that average is the standard one that is used. So it is when both classes can have 50 percentage of the data points. So what is the Gini index for a node containing only one class, which is called as a pure node? So is it 0.510 undefined? So for Gini, we calculate it as 1 minus sigma, the probability of each class squared. So here I have mentioned it is a node with only one class. That means this probability of that class will be 1 and probability of all the other classes will be 0. So then what happens is 1 minus uh, 1 square plus 0 square plus etc. So then it is 1 minus 1, that is 0. So the answer is 0. So pure node will have Gini index value of 0, which indicates minimum impurity. Now here also this entropy you can calculate with the help of formula. So entropy is given by minus sigma, the probability of a class. So it's over all the classes, probability of the class into the log of probability of class. So here, this probability, it will be maximized. I mean, this entropy will be maximized when all the classes are equally likely. And if we take binary classification, all the classes are equally likely when the probability is 0.5. So when we substitute that here, suppose if I have a binary classification, then I'll have two classes. Each class's probability is 0.5, 0.5. Then if I substitute this here, what I will get is minus zero point 0.5 into log 0.5. Again, minus zero point 0.5 into log 0.5. So this is minus zero point 0.5 into, if you calculate this, you will get 1. That means that this is the most impure state. That is, it is the most uncertain state. It is like you end up in a node A where you have 50 percentage of class A and you have 50 percentage of class B. So this is the most impure node. So that is the meaning of that. At a node with 8 S and 4 no samples, totally there are 12 samples. What is the entropy H before split? So entropy is given by minus sigma over the different classes Pc into log Pc. So there are two classes, yes and no. The probability of yes is 8 yes and 12 samples. So it is 8 by 12 and no is 4 by 12. So this is that probability that you have to substitute. So it is when you do this calculation, you will get 0.92 approximately. What is the k-means cost function W minimize? The maximum distance between any two points on the dataset, the total between cluster variance, the total within cluster distance, uh, the entropy of cluster assignment. So it reduces the total within cluster distance, which is the total square distance from each point to its own cluster center. So it is the total cluster within distance. The elbow method is used to choose the k in k-means. What does the elbow mean? Yeah, so the elbow is the point at which additional clusters will not give any improvement in the W value. Now coming to the previous year assignment questions. So you can read the first question. So the first question is, what is the main problem with decision trees that bagging helps to address? Low accuracy, high computational cost, high variance, inability to handle categorical data. So the answer is here, high variance. So in the solution that is given in the previous years, they have mentioned that bagging addresses the high variance problem of decision trees. And the individual decision trees tend to overfit to their training data. But by combining predictions from multiple trees trained on different bootstrap samples, bagging reduces the variance and improves the generalization. In k nearest neighbors, what does k parameter represent? The number of features to consider, the number of nearest neighbors to consider for classification, the number of clusters to form, number of iterations to perform. Yeah, so k is the number of nearest neighbors to consider for classification. So when a new neighbor comes, we find k number of neighbors before taking a decision on the output. In gradient boosting, what is fitted in each iteration? A completely new model independent of previous iteration, the original target value, the gradient of the loss function with respect to predictions, the inverse of loss function. So in gradient boosting, the algorithm try to reduce the error uh, by reducing the error from the from the previous one, but with respect to the current prediction. So each new model is trained to predict the, so as given in the last year solution. So in gradient boosting, each new model is trained to predict the gradient of the loss function with respect to the current prediction. So it will iteratively reduce the error by following the direction of steepest descent. So it will find the loss if y is the actual value, and f of x is the prediction. Then f of x is the current prediction. Then the next model will be trained to approximate the loss between y and f of x with respect to f of x, which is the current ensemble prediction. So the next model will work on this one. What is typically chosen for the number of features to consider at each split in a random forest? Square root of the total number of features, logarithm of the total number of features, all the features, half of all features. So it is the square root of the total number of features. In AdaBoost, what happens to data points that are misclassified in an iteration? Their features are transformed, they are assigned to a different class, they are removed from the dataset, they are given higher weights in the next iteration. Yeah, so in AdaBoost, it starts with an equal weight to all the classes, but then gradually, based on the misclassification, it will increase the weight in the next iteration. So that the subsequent learners will focus more on the difficult example. Which loss function is associated with AdaBoost? Cross entropy loss, hinge loss, mean squared error, exponential loss. Yeah, so it is exponential loss for AdaBoost. Which metric is not typically used to make splits in binary decision tree? Gini index, entropy, classification error, mean squared error. Yeah. So mean squared error is not typically used to make split in binary decision tree, but Gini index, entropy, classification error, all these are used. In k-means clustering, how are cluster centers typically initialized? Using the first k data points at the center of the data sets, using principal component analysis randomly within the range of data. So in k-means clustering, how are the cluster centers typically initialized? How are the k different cluster centers formed? No, so how k-means work is you have suppose a data set like this. Okay, so these cross marks are some uh, data points. How k-means work is, so I know that there are four different groups or clusters here, but in case of real data set, I will not know that there are four different clusters, cluster 1, cluster 2, cluster 3, cluster 4. I will not know this, but I will just assume that there are k clusters and I don't know what these k values are. So I will do, for example, the elbow method, and I found that the value of k is 4, for example. Then how do I select, or how do I do the initialization of the four cluster center? I will randomly select some cluster points. I mean, I don't know which is the cluster center, so I will randomly select 4 points as my uh, cluster center. So that means I can select, for example, this one, this one, this one, and this one. It's a very random choice. Or I can select this one, this one, this one, this one, all four of them from the same cluster. Or I can select this one, two from this and two from that. So it is a random selection of like initially we select random number of sorry, not random number. Initially we select randomly within the data. So the answer is we select the cluster centers randomly within the range of the data. What is a dendrogram in the context of hierarchical clustering? A histogram of feature importance, a graph showing the evolution of the cost function, a tree-like diagram showing the hierarchy of clusters, a scatter plot showing cluster assignment. So at each step of the hierarchical clustering, this dendrogram will tell you how the clusters are like split or it is merged, um, and this is like a tree-like diagram that show this hierarchy of clusters. So it's a tree-like diagram showing the hierarchy of clusters. A key advantage of hierarchical clustering over k-means is it doesn't require specifying the number of clusters beforehand. It works better with categorical data. It is always faster. It always produces better clusters. So as given in the solution, a key advantage of hierarchical clustering is that it produces a complete hierarchy of clusters. Users can choose the appropriate number of clusters after examining the dendrogram, unlike k-means, which require specifying the number of clusters k in advance. So it doesn't require specifying the number of clusters k in advance. That is the benefit of this. Okay. So those are the previous year assignment questions. Now, So why does k-means require multiple random reset? That means why do we have to start why do we have to do k-means multiple times with a different initialization of those k values? Yeah, so because different initialization will lead to different local optima, and the best is chosen by taking the lowest within cluster distance. What does bootstrapping means in the context of bagging? Training on a clean, balanced version of dataset, creating a new dataset by sampling the original one with replacement, splitting the data into equal sized folds, removing outliers. Yeah, so it is creating a new dataset by sampling the original one. So in the k-means update step, how is each cluster centroid calculated? As the mode of points in the cluster, as the point with the minimum distance, as the mean of all data points currently assigned to that cluster, as the point closest to previous centroid. Yeah, so it is the mean of all the data points assigned to that cluster. So in KNN, what is used as the default metric? So the distance metric that is typically used is uh, Euclidean distance. What is the primary problem with single decision trees that bagging aims to solve? Low accuracy on training data, high variance, small changes in the training data can cause large changes in the model, high computational cost, inability to handle numerical features. So decision trees, they are high variance model. A fully grown tree will memorize the data set, like the training data. So if you give it a different training set, it will process a or it will produce a very different tree. So bagging will reduce this variance by averaging over many trees. What is the main trade-off of random forest compared to single decision tree? Higher training time but lower accuracy, better generalization performance at the cost of interpretability, lower variance but much higher bias. Random forest cannot handle multi-class problem. So, single tree, if you take, it has readable rules at each of the node. But in random forest, we have many trees, for example, hundreds, 500s of trees, and each uses a different subset of features, and we aggregate over these trees. So there is no single decision path in random forest. So the interpretability is difficult compared to a single decision tree, but it will have better generalization performance. So the answer is better generalization performance at the cost of interpretability. Okay, thank you all for attending today's class. We'll meet next uh, Tuesday for week 10 session.